Hi, and welcome again to a video for CS360. And so in this video, we will cover the Myhill-Nerode theorem. And this is yet another property of regular languages. And in particular, it can be used as a technique for showing that a language is not regular. And this one is actually a characterization of regular languages. So you can view it as yet another characterization of regular languages, similar to regular expressions or DFAs or NFAs. And so while the pumping lemma sometimes fails, sometimes it cannot show a language is not regular. So there exist non-regular languages that satisfy the pumping lemma. So you cannot use the pumping lemma to show that these languages are not regular. The Myhill-Nerode theorem will never fail to show that a language is not regular. It will just sometimes be tricky to use. In other words, it's a full characterization of the regular languages. And the characterization is as follows. So first, we need to define an equivalence relation. Fix a language A. And then, so we say that X, or actually, let's write it like this. We say that a string X is equivalent under A to Y. Okay, is equivalent to Y with respect to A, where X and Y are arbitrary strings, not necessarily strings in A. If there exists a string Z, okay, that's also an arbitrary string, such that one of X, Z, and Y, Z is in A, and the other isn't. Okay, so so Z in that case is called, or I should say such Z, a distinguishing extension. Okay, so X and Y are set, sorry, this is wrong. We say that X and Y are not equivalent if there is a distinguishing extension. Okay, so X is not equivalent to Y if there's a distinguishing extension. Okay, so if there does not exist such Z, then X is equivalent to Y. Okay, so this funny looking definition, it's kind of meant to correspond to whether X and Y reach the same state in the DFA for A. So consider a DFA for A. Consider running it on X and you reach some state, and consider running it for Y and you reach potentially another state. If you reach the same state, then it means that no matter what other string you will read, you will still reach the same state. So if you reach the same state P when you run the DFA on X and also when you run it on Y, if in both you reach state P, then when you run on XZ and on YZ, you still reach the same state, right? Whatever state you reach after reading Z starting from P, right? So after X, you get to P, then you read Z and you get to, say, Q. After Y, you also get to P, so then you read Z and you must still reach Q, okay? And because you reach the same state when reading both XZ and YZ, then that state is either accepting or not accepting, right? So it's not possible for one of XZ and YZ to be in A while the other isn't, if the DFA is a DFA for A. Okay, so if X and Y are equivalent, so X and Y being equivalent is supposed to mean that intuitively it's supposed to correspond to X and Y reaching the same state in the DFA for A. Now, formally, if you try to prove it, this will only be true under the assumption that this DFA is the minimal DFA for A, that there are no kind of wasted states that don't really that are duplicates of other states, for example, or that don't really do anything. But for the minimal DFA for A, the smallest DFA, the one with fewest states, it turns out, first of all, that such a DFA is unique. There's only one smallest DFA for A. And second, that X and Y are equivalent. So we have X equivalent to Y under A, if and only if the minimal DFA for A gets to the same state when run on X and when run on Y. Okay, so anyway, so the Myhill-Nerode theorem. So first we've defined an equivalence relation here, okay, which kind of talks about whether X and Y are equivalent, which is, we should think in the back of our heads that means whether they reach the same state when you run the DFA on these strings. Okay, and what the Myhill-Nerode theorem says is, now if you group the strings, if you partition sigma star into the equivalence classes for this equivalence relation, so you look at all this, like, so we have an equivalence relation here, right? We say two strings are equivalent, you know, if there's no distinguishing extension between them, right? So given this equivalence relation, we can partition sigma star, the set of all strings, into the equivalence classes, into all the strings that are equivalent to each other. That's one class, and there, maybe there's three classes, maybe there's one class only, maybe all, you know, maybe all strings are equivalent, or maybe no string is equivalent to any other. So there could be infinitely many classes for sigma star. And what the Myhill-Nerode theorem says is that the language A is regular if and only if there's finitely many equivalence classes in sigma star. Okay, so the partition of sigma star into the equivalence classes has finitely many parts. Okay, there's finitely many classes. So in particular, the Myhill-Nerode theorem says that if there exist strings x1, x2, you know, infinitely many strings in sigma star, such that xi is not equivalent to xj under A for all ij in n with I not equal to j. So for with I not equal to j. So if no pair is equivalent to each other, and you have infinitely many such strings that are no two of which are equivalent, then A is not regular. Okay, you know, but if there exists a finite sequence, so if there exists x1 up to xn, up to xn, so this is a finite number of them. This is in sigma star for some n in n. So this is for a finite number n, such that for all y in sigma star, for any string that you pick in sigma star, there exists I such that y is equivalent to xi. So if you can find finitely many strings such that every other string is equivalent to one of them, then A is regular. Okay, so basically, if you can show there's only finitely many equivalence classes, so you can find finitely many strings such that any other string is equivalent to one of them, then A is regular. But if you can show that there's infinitely many equivalence classes, so if you can find infinitely many strings, no two of which are equivalent to each other, then A is not regular. Okay, so one of these two cases must hold. You know, either there's finitely many equivalence classes or there's infinitely many equivalence classes. And the Myhill-Nerode theorem, you know, tells you that A is regular in one case and not regular in the other case. Okay, and so you can use this to show that the language is not regular. You can also use it to show a language is regular, but of course, if you're just trying to show a language is regular, might as well just construct a DFA or NFA, I guess. Usually this is not necessarily as simpler than constructing an NFA, let's say. But to show a language is not regular, then this can be a convenient way to do so. So let's see if we can just give our usual example. So let's say that A is 0 to the n, 1 to the n. This is our favorite non-regular language. Okay, so let's see if we can, so come up with infinitely many strings, no two of which are equivalent. So let's say our infinitely many strings are going to be 0 to the I, the string 0 to the I for all I and n. Okay, so this is infinitely many strings. Okay, now they're not in A. Well, I guess the first one, epsilon, the empty string is in A, but the rest are not in A. That's okay. Okay, the Myhill-Nerode theorem, you're allowed to pick infinitely many strings. They don't have to be in A. They're allowed to be in A, but they don't have to be. We just need to show that no two are equivalent under the equivalence relation of A. So let's pick two of them. Okay, so let's pick two of them. So let's pick, let's pick I not equal to J, and we look at 0 to the I versus 0 to the J. And we want to show they're not equivalent. So that means we want to find a distinguishing extension Z. So we want to find Z such that 0 to the I Z is not equal to 0 to the J Z. Okay, and we can pick Z equal 1 to the I. And in this case, the two strings are 0 to the I, 1 to the I, and 0 to the J, 1 to the I. Now, note that 0 to the I, 1 to the I is in A. Okay, but because I does not equal to J, right, then we have 0 to the J, 1 to the I is not in A. Okay, so then this is, distinguishing extension. And that's for arbitrary I not equal to J. For any I and J that are not equal, we can find a distinguishing extension. Okay, so we conclude that A is not regular. Okay, fairly simple, arguably even simpler than the pumping lemma, and it's kind of guaranteed to always work. So when you're showing that a language is not regular, you're welcome to either use the pumping lemma or you can use the Myhill-Nerode theorem.